we can get into the next chapter, acid-base chemistry, which is also quite chem stuff. But I don't think we can finish up all the stuff that we must cover up with this chapter. So probably next week we'll finalize the acid-base chemistry chapter as well, and then getting into the intro for the organic compound. So last time we discussed the molecular theories, and today we'll discuss the hybridization of atomic orbitals, and how these theories and how these theoretical framework can be used to describe the bonding exists within the molecule, the organic molecules, right? So we'll describe how single, double, and triple bonds can be described within the framework of the hybridization theories, okay? So I guess we finished, we stopped here after we learned about the perspective formula, ball and stick model, space filling model, and electrostatic potential map, which are all presentation method for the given molecule. And the exemplary, the example given here is the methane molecule, right? So you know, it's a tetrahedral geometry. And with the perspective formula, you can basically draw the 3D structure in the plane in your paper, right? So this solid line indicated bond in the plane. Okay. So this carbon, hydrogen, two hydrogens actually. Right? These three elements are given in the plane in your paper. The solid wedge here indicate the bond protruding out from that plane, from your paper, right? This hydrogen, so you can think about this hydrogen is locating above the plane. The hedged wedge here indicate the bond projecting back, okay, backward. So this hydrogen located below the plane for your paper, right? That's how you can see the 3D structure or tetrahedral geometry in this particular case with this perspective formula, okay? And we discussed what is ball and stick model and space filling model and electrostatic potential map last time as well. Right? But the thing is, like for the methane molecule, right? You know that all four C bond in methane, right? They're all equivalent. Right? All C bonds are identical. In other words, their bond length is given here as 1.1 angstrom. And bond angle is also given, right? 109.5 degree, the typical number for the tetrahedral geometry. So the goal is here with the orbital theory, particularly hybridization orbital theory, to rationalize this geometry. Right? That is the goal. And then I'm pretty sure you guys all know about the hybridization theory already. This is origin chem stuff, but for the OChem course, OChem 1 and OChem 2, you better review what is hybridization theory. 그래서 지난 시간에 이야기한 것처럼 유기화학 분자의 구조나 반응성을 describe 하는데 hybridization theory가 가장 frequent하게 많이 쓰이기 때문에 여러분들이 아마 다 배웠겠지만 고등학교, 대학교 과정 거치면서 젠캠 코र्स 거치면서 다 배웠겠지만 한번 다시 리뷰를 할 필요성이 충분히 있습니다. 하이브리다이제이션 theory는 지금 메인 그룹 엘리멘트를 포함하는 화합물에 아주 잘 적용되기 때문에 카본과 하이드로젠, 나이트로젠 컨테이닝, 옥시전 컨테이닝 모레큘에 잘 적용이 되기 때문에 유기화학에서는 아주 유용하게 쓰입니다. 그럼 이제 대상이 바뀌게 되면 하이브리다이제이션 theory도 완벽하진 않기 때문에 또 다른 theory가 필요하지만 적어도 유기화합물을 다루고 유기화합물 간의 반응성을 논할 때에는 hybridization theory가 아주 유용하다. 그래서 저희가 많이 사용하게 됩니다. Okay? So again, for the organic molecules and its reactivities or reaction between two or three different molecules, the organic molecules, the hybridization theory is very, very useful. That's why we here, right, reviewing this theory. So we are first learning about the sp3 hybridization to rationalize how the methane molecule, right? Why methane molecule, or to explain the geometry of the methane molecule using the hybridization theory. Okay, that is the goal here. So As you know, right, methane molecule, the center carbon, sp3 hybridized. So what that means is that you are mixing up these 4 orbital, okay? S and 3 p orbital set. They can be hybridized, right? And for the electron configuration, you can maybe think about, right, one of the S electron, they can be promoted. Right? So you can maybe compare before promotion and after promotion. Right? After promotion, right, each orbital set, S and p orbitals, they have 1 electron. So if you think about carbon, right, carbon has only 2 unpaired valence electrons. If you think about the periodic table, but in many cases, right, in all cases actually, for the organic molecule, carbon has to have 4 covalent bonds, right? So we need the promotion, right? So with this promotion now, right, you can have 4 unpaired valence electrons, right? And then you can hybridize, right? So you have 4 orbitals, S and 3 p orbitals, and after hybridization, they'll become all equivalent, right? Each of them will become sp3 orbital, and in that you have 4 sp3 orbitals, right? 4 hybrid orbitals can be formed after hybridization process, right? So hybrid orbitals basically result from combining the constituent atomic orbitals, in this case S and p orbital sets. As you guess, right, each sp3 orbital has 25% S character, okay, and 75% p character. Right? And visually, right, you can guess how sp3 hybridized orbital looks like. So this is the process of the hybridization. You have 1 s orbital and p orbitals, right? And if you're mixing this 2, then you can maybe intuitively rationalize how the orbital looks like after hybridization. You have some promotion part, the s orbital, for instance, as to the lobe of the original p orbital, right? That's why you're seeing the addition here. But the bottom part, you can guess, right? Must be deduction, right? Or subtract from the outer lobe of the p orbital, okay? To form sp3. And then you will see later the larger lobe, right? The green part can be used to form the covalent bond with the other element or other atomic orbitals, right? Like maybe s orbitals in hydrogen. Okay. Right. So you can apply this concept, right? So we discussed below, right, how S and p orbital can be summed up, right? And you can apply this to the sp3 hybridization, right? For which you need 1 s orbital and 3 p orbitals, right? And after hybridization, right, since you're mixing 4, the outcome is also 4. Right? So you are having 4 sp3 hybridized orbitals, and how this is how sp3 orbital basically looks like. You may notice that, right, s orbital in this picture is more stable than p orbital, but sp3 orbital is basically in the middle, right? So you can maybe see the vertical location, which is showing you the energetics, the relative energetics. So sp3 orbitals, generally speaking, more stable than the p orbital, but less stable than s orbitals, somewhere in between. And the 4 sp3 orbitals will adapt the spatial arrangement that keeps them as far away from each other as possible. Right? So you probably know about the VSEPR theory or VSEPR model, right, to minimize the hindrance. Right? Each of the sp3 orbital should locate or keep them as far away from each other as possible. Right? So that's how, right, sp3 orbital, 4 sp3 orbitals locate, right, center around this central element, the carbon. Right? Okay, so 4 sp3 orbitals. reside as far apart as possible. And in this picture, in this presentation, this small lobe, right, smaller lobe here, okay, are omitted. Okay. And then this is the sp3 overall set from carbon, and you also need to consider the 1s orbital given for hydrogen, and then the 1s orbital, right, from hydrogen, and sp3 orbitals from carbon, right? They can form the covalent bond, and that's how you can rationalize the geometry of the methane molecule, right? All 4 CH bonds has to be equivalent or identical, right? The bond length is 1.0 angstrom, 1 angstrom, equivalent for all CH bond, right? Symmetrical, or tetrahedral geometry can be rationalized with, right, this sp3 hybridization model. You can also think about ethane, right? The structures and MOs of ethane can be imagined, right? And this is the perspective formula for the ethane molecule. You have one more carbon, right? C2H6 molecule, fully saturated molecule. And each carbon, basically, if you're seeing this molecule with respect to the center carbon, that's also tetrahedral structure, right? And there's one more bond actually between carbon and carbon, and this bond can be described as a sigma bond between sp3 and sp3 orbital from each carbon. And other bonds are basically same, can be described as identical as you did for the methane molecule. The bond between carbon and hydrogen, sp3, and 1s orbital from hydrogen, right? The covalent bond can be described with this model. And by the way, this is the ball and stick model of ethane, the staggered conformation state. We'll learn a lot about the conformation state in the next chapter. But for now, you can accept why this should be the most stable structure for the ethane. Right, so as a simple practice, you can solve the quiz here. What orbitals are used to form 10 sigma bond in propane? Okay. The bottom one, explain why sigma bond formed by overlap of s orbital, but sp3 orbital with carbon is stronger than sigma bond formed by overlap of s orbital with the p orbital of carbon. Top one is easy, right? You have 3 carbons, right, within the propane. So you have 2 sigma bond between, right, sp3 hybridized orbital from carbon, right? And 1, 2, 3, 1, 2, 3, 1, 2, 8 sigma bond between 1s hydrogen, right, orbital, and sp3 hybridized orbital from carbon. So in total, you have 10 sigma bonds. And we'll learn about this later, but if you think about, right, the consequence of hybridization and maybe degree of the overlap when the bond is formed, right? If the orbitals, right, this is generally speaking, if your orbital, the participant orbitals has higher S character, that leads to higher overlap, right? So the first sigma bond is the bond between S and sp3 orbital, right? The second sigma bond, right, is a sigma bond between S and p orbital, right? So if you think about the S character of this pair net, right, you know that the above one has a higher S character. The larger the S character, your orbital will look more like a ball, and it's more prone to have, right, the larger overlap, and that leads to the stronger bond. Okay. 아마 뒤에서 조금 더 다룰 텐데 본드의 스트렝스를 결국 비교해 보라는 거죠, 그렇죠? 그러면은 결국 얼마만큼 오비탈 오버랩이 강하게 일어나느냐, 또 척도가 될 수 있겠죠. SQQ가 높을수록 S 오비탈의 색깔이 더 더해지는 거라고 생각을 하게 된다면 더 구 모양에 가까워질 것이고 구 모양과 구가 인터랙션 하게 될 때 오버랩이 더 커진다. 그렇게 생각을 하시면 SQQ가 높을수록 오버랩이 커지고 본드 스트렝스가 강해지겠구나. 이렇게 예상을 하실 수가 있겠죠. Alright, that was the SP3 hybridized model. What about the other hybridization model, right? SP2 or SP hybridization? That's the next topic, and maybe as a good example, the exemplary molecule, we can think about the ethylene. This is how ethylene looks like, right? You have the double bond between these two carbons. Okay? So to explain, rationalize the geometry of this molecule, you need the SP2 hybridization. Okay? The ethylene basically have a planar structure, so all elements, right, carbon and hydrogen, be located in the plane or paper, in your paper or slide, right? It's a planar molecule, and the bond angle is around 120, right? So how can we explain this, right? The hybridization model. And you probably already know, right? This double bond consists of one sigma bond and one pi bond. And as I mentioned, right, for explaining the geometry of this ethylene molecule, you need sp2 hybridization. Okay, so this is again the s and p orbital set, the original orbital set. And for the sp2 hybridization, you only need two p orbitals, right? So one s orbital and two p orbital, they can get hybridized. Since you are using three orbitals, the outcome is also three. You're going to have three sp2 hybridized orbitals, in this case sp2 hybridized orbitals. And each sp2 orbital will have 33% of s character and 67% of p character. The last amount of the p character as compared to sp3, right? Hybridized orbital. And there is one remnant, the p for this model. Okay. And with this hybridization, right, with this tool, now you can have, right, three equivalent, right, sp2 hybridized orbital, right, which are located in, right, the same plane. Right? So you can maybe view this sp2 orbitals from the top. Then you can notify the triangle or a trigonal plane exists. Right? This is from this sp2 hybridized orbitals. And again, following the VSBR theoretical model, these three sp2 orbitals reside as far apart as possible to minimize the hindrance. That's why this trigonal planar, right, structure can be given. And then, as I mentioned, there's one remnant p orbital exists, right? And these p orbitals stand perpendicular to the plane formed by sp2 hybridized orbital. Okay? So you can see this purple remnant p orbital from top, right? Well, and this is how sp2 hybridized core accommodate three sp2 hybridized orbitals and one remnant p orbitals. Okay. So 뭐 이름이 알려주듯이 sp2라고 하면 s 하나, p 두 개가 하이브리다이즈 되는 건데, 카본은 원래 p 오비탈이 3개잖아요, 그죠? p 오비탈 3개 중에 하나가 그러면 남게 되죠. 남게 되는 거를 이 purple 하이라이트 돼 있는 포지션에 이제 위치시키게 되면 돼요. 그래서 sp2 오비탈은 같은 플레인에 있으면서 각각의 꼭지점을 향해 배양이 되어 있는 거고, 그렇게 형성될 플레인에 수직 방향으로 p 오비탈이 하나, 남은 p 오비탈이 하나 서 있다라고 생각하면 되겠죠. 그게 그 센트럴 엘리먼트 기준에서 보는 오비탈의 배양이 되겠고, 이제 그 센트럴 엘리먼트 주변에 다른 엘리먼트들의 오비탈과 이제 트랙션을 하면서 본딩을 형성하게 되겠죠. 오케이. So we can then explain, right, with this sp2 hybridization, the geometry of the epsilon. Right? So you have the central carbon. Right? So this is how it looks like. Right? So you have this central carbon here and there. Both of them are sp2 hybridized. And as a result, we have 1, 2, 3 sp2 orbitals, sp2 hybridized orbitals for the left carbon, and you're going to have sp2, 3 sp2 orbitals for the right hand side carbon as well. Right? Then you can explain or predict there are going to be one sigma bond between sp2 and sp2 orbital, right? And that is actually sigma bond. And there's another sigma bond between carbon and hydrogen as well, right? So you have sp2 orbital, right, for the carbon, and 1s orbital for hydrogen. So these two orbitals will interact in forming the carbon-hydrogen bond, the sigma bond, right? But in this picture, the p orbital is omitted, but you can maybe see the side view. From the side view, you can notify here there is a remnant p orbitals, right, located perpendicular to the plane we just described on the left hand side, right? And this p orbital, right, the perpendicular p orbital can formulate the pi bond, right? The side to side, right, interaction, and that is formulating, right, one pi bond, and that's why, right, ethylene has one sigma bond and one pi bond. Sigma bond between two sp2 hybridized orbitals and one pi bond between two p orbitals, okay, the remnant p orbitals. That's how we can rationalize, right, the double bond within the ethylene molecule and also the geometry of the ethylene molecule. Okay. Letter Creech, do the sp2 carbons and the indicated sp3 carbons have to lie in the same plane or not? What is the second one? Do the sp2 carbons and the indicated sp3 carbon lie in the same plane? Same question, but at a different molecule. Alright, if you apply the basic principle, it's just learn for the sp2 hybridization, you can get an easy answer, right? You have first you can notify the double bond, location of double bond, right? Which means this carbon and these carbons are sp2 hybridized, right? So a central element for the sp2 hybridization, right? Then from this center and this center, you can think about the plane, right? The planar elements or construct. So maybe you can draw the triangle like this, right? Which means this moiety, right, has to be in the same plane. You can also draw from this central carbon, right, the plane, triangular plane. Then you know that this carbon and this carbon has to be in the same plane. Because these are in the same plane, and these are same plane. These and these are same plane, and these should locate in the same plane. By which, right, you know that these two has to be on the same plane. And do the same thing for the B, right? This carbon, your center element for the sp2 hybridization. So you can then draw the triangle, right? Like this. And all this element has to be in the same plane, but not necessarily this carbon, right? So the answer is no for B, right? The answer is yes for A. For the bottom one, do the same thing. You first notify the location of the double bond, right? Just here. And then you must know that there's a hydrogen, right? The bond is omitted in this, right, notification. And you can apply the same thing, right? So from this carbon, you know that these are all on the same plane, and these are also all in the same plane, not necessarily this carbon. What about this one? You can do the same thing. Triangle, triangle. So you know the answer then. Okay? This carbon and this carbon has to be in the same plane. What about this one? From this double bond and from this carbon, you can draw this triangle, the trigonal plane, and from this carbon, you can do the same thing. Okay? So you know that then these and this has to be in the same plane. Right, what about the triple bond, right? For describing and explaining or predicting the triple bond, you need to invoke the sp hybridization, okay? Not the sp3 or the sp2, not the sp. Okay, and this is a typical exemplary molecule. Acetylene, it has triple bond here. This is linear molecule. Okay. Bond length is 1.2 angstrom, by the way, between two carbons. And you already know, right, that this triple bond is composed by one sigma bond and two pi bonds, right? So how we can rationalize this, what the hybridization will tell. That's the goal. And for the triple bond, as I mentioned, you need to invoke sp hybridization, which means you need one s orbital and one p orbital, right? Since input is 2, outcome is 2, right? So that's why you're having 2 hybridized orbital, 2 hybridized sp orbitals. And then, right, you can count the remnant p orbital, right, which is in this case 2. You have 2 remnant p orbitals, okay? Like sp2 hybridization, right? In that case, you only have one perpendicular p orbitals, okay, right? And for the sp hybridization, you can count down, right, the character, s character and p character, which is big T and big T. Okay. So with this settings, right, then you can describe the triple bonds, right? And problem is you can imagine, right, you have one sp orbital set and 2 perpendicular sets, right? 2 perpendicular p orbitals, okay? And two sp orbitals reside as far apart as possible, and the only way to do so is being linear, right? So you have sp orbitals one side, the sp orbital the other side, right? And as you know, right, you have 2 perpendicular p orbital set, in other words, right? What's located, right, perpendicular to each other, right? So you have now 2 p orbitals, what the purple highlight here, okay? And this is the orbital set given for the center carbon, right? And then you can use this orbital to describe the bond, right, between the elements, okay? So between, I can write down the structure of the acetylene here. So you have the center carbon here and there, right? And you have sp orbital, right, here and there. You can then describe one sigma bond between 2 carbon, right? The sp and sp overlap, right? And of course, you have one more, actually 2 more sigma bond here, right, between carbon and hydrogen. This can be described as 1s and sp orbital, sp and 1s orbital, right? this can explain the sigma bond between carbon and hydrogen, or hydrogen and carbon. And as we saw in the previous slide, you have two remnant p orbital set, right? Here and there, right? And each of them, right, can formulate the side to side or side by side interaction. So you can guess, and there must be two pi bonds, right, within two carbons. Okay, so blue and purple, right, each give you one pi bond respectively. So in total, C will give you how, right, the bonding interaction can be made by the orbital set. Okay, the yellow or orange indicate the bond between the sp orbital, right? So it's a central yellow lobe indicate the covalent bond between sp and sp orbitals, and the bond between carbon and hydrogen again can be described with the sp orbital and one s, okay, orbital from hydrogen, and blue purple corresponds to the pi bond, right, between p orbital from each carbon. Okay, so we're going to have one sigma and two pi bond, and this will give you triple bonds, right? Exist within the acetone molecule. Right? 그래서 뭐 복잡할 거 없죠? 트리플 bonds SP 모델 적용하게 되면 SP와 SP 사이에 시그마 번드 하나 있을 거고, 그렇죠? p 오비탈 셋이 두 개가 남으니까 각각이 파이 번드 형성하는 시그마 하나, 파이 두 개, 그래서 세 개, 삼중 결합이 설명이 되겠죠. SP2는 아까 설명드린 것처럼 SP2와 SP2가 시그마 번드, 그렇죠, 형성할 거고, 그 경우에는 이제 랩는 p 오비탈 셋이 하나 있어서 파이 결합이 하나 가능해지겠죠. 시그마 하나, 파이 하나, 이렇게 이중 결합을 설명하면 되겠죠. SP3는 p 오비탈 셋 남는 거 없었고, SP2와 SP3 간의 결합밖에 없었죠. SP2와 SP3의 오버랩에 의해서 하나의 시그마 번드가 카본과 카본 사이에 형성되겠죠. 단일 결합이 그렇게 설명이 되겠습니다. 그렇죠? 그럼 이제 카본 컨테이닝 organic molecule에서 결국 등장하는 게 다 뭐 단일 결합, 이중 결합, 아니면 삼중 결합, 99.9% 그렇게 설명이 됩니다. 그래서 SP2, SP3 hybridization 모델로 따라서 지오메트리와 일렉트론의 population 정도를 다 예측 혹은 설명이 가능해지니 hybridization 모델이 이제 강력하다라고 이야기할 수가 있겠죠. Alright, what is this? This is a simple way to determine the degree of hybridization. Right? This is a small t, right? So these are maybe the given molecule, right? And you can try to count the number of arms. 팔의 개수를 세란 얘기인데, 그렇죠? 하나의 암에 해당되는 그 한 개의 카운트되는 것이 이제 싱글 번드가 몇 개 있냐, 혹은 더블 번드가 몇 개 있냐, 트리플 번드가 몇 개 있냐, 론 페어가 몇 개 있냐, 그렇죠? 그 각각이 하나로 카운트가 된다는 이야기입니다. Okay? So one arm can be a one single bond, right? Or one double bond, or one triple bond, or one lone pair. Okay, so you need to be careful about the unit here. Okay, so if you count up all the number, right, all the number of arms here, and if that number is 4, then you can answer, right? You can get the answer for the hybridization of that central atom is sp3. Right? If the number is 3, then the central atom must be sp2 hybridized. If the number is 2, then the central atom must be sp hybridized, right? So you can take an example here of the methane. You can count the number of arms, right? You have 1, 2, 3, 4 single bond, right? So the total number must be 4. There will be no double bond, no lone pair, right? So you know that the central carbon is sp3 hybridized. What about this carbon? You have 1 single bond, second single bond, and 1 double bond, right? So from this perspective, from this carbon's perspective, you have 3 arms, right? So you have sp2 hybridization for this carbon, okay? what about this example? You have one on and second on, one single bond, one triple bond. So in this case, you have the two arms, and from which you can conclude this carbon, this center carbon must be sp hybridized. 그렇죠? 카본 있는 경우에는 론 페어가 없었고, 이제 론 페어가 있는 경우, 오크시즌이나 나이트로젠이 있는 경우에 론 페어까지도 하나의 단위로 인식하셔서 개수를 세시면 토탈 암의 개수를 이제 세실 수가 있어서 그 토탈 암의 개수를 가지고 4, 3, 2 중에 하나에 들어갈 텐데 그걸 가지고 sp3냐, sp2냐, sp냐를 결정하시면 되겠습니다. There's a special case, the reactive carbons, and the rule apply for this case too. And we'll learn about the carbocation the next maybe a few chapters later, and carbon radical. We'll learn about the radical chemistry in OChem2 though, right? But you know what its radical is, right? And then carbon anions, right? And for the carbocations, right, you can describe the center carbon as sp2 hybridized, right? Center carbon is sp2 hybridized. There's a remnant p orbital, and which is empty, by the way. That's why this is a cation, right? You are compared to the methane. You can okay compare the geometry of this species as well, carbocation. So you can see the, for instance, metal cation angle side view. This is a plane. From top view, you can use the trigonal plane. You should know that there is a remnant p orbital which is empty. There's no electron. What about metal radical? This is also sp2 hybridized. So from the angle side view, you can notice the plane. From top view, trigonal plane can be notified. And in this case, again, there's a remnant p orbital, which is occupied with the one electron. Right? There's one single electron reside on this p orbital, right? And this is how a metal radical can be described with the hybridized form. You can also think about the anion, right? The anionic case, the metal anion, for instance. In this case, right, you have one lone pair. Right? So applying the rule we just described, right? Then there's a one lone pair, so you have to count the number of arms. Right? So 1, 2, 3, 4 arms. So the center carbon must be sp3 hybridized. So in this ballistic model, right, you can guess, right, there's a one sp3 orbital exists and lone pair is sitting there, 2 electron, right, sitting there. So this lone pair is residing on sp3 orbitals. Okay? And then you have to describe the bond between this carbon and hydrogen as sp3 and s orbital. But the above two cases, metal cation, metal radical, the center carbon is sp2 hybridized. Thus, the bond between this carbon and hydrogen should be described as a overlap between sp2 hybridized and s overlap for hydrogen. So carbocation, carbo radical, carbo anion. 이제 6.2 수업 들으면 이제 종종 등장할 스피시스들인데 각각의 지오메트리가 어떻게 디스크라이브 될 수 있는지 오늘 배운 하이브리다이제이션 모델로 다 설명이 가능하다 이야기입니다. 카보 캐라이언, 카보 라디칼은 센트럴 카본이 sp2 하이브리다이즈 되어 있어서 이제 삼각 구조, 삼각 평면을 이제 카본과 하이드로젠이 형성하고 랜덤 p 오비탈이 이제 퍼펜디큘러하게 로케이션 되어 있을 때 거기에 일렉트론이 앉아 있으면 카보 캐라이언 되겠죠. 그렇죠? 일렉트론이 하나만 있으면 이제 라디칼이 되는 거예요. 근데 이제 카본 애나이온이 되면 이제 론 페어가 형성이 되죠. 일렉트론 두 개가 있으면 이제 페어가 되는 거잖아요, 그죠? 페어가 되게 되면 이제 센트럴 카본의 지오메트리가 테트라헤드럴 스트럭처로 바뀌게 됩니다. 이렇게 됐을 때 이제 이 캐라인이 아니라 N아이언의 지오메트리를 이제 저희가 제대로 기술하기 위해서는 이제 sp3 하이브리다이즈 모델을 적용해야 되고, 따라서 론 페어 또한 sp3 하이브리다이즈 오비탈에 해당된다. 오비탈에 들어가 있는 전자다라고 기술을 해야 되는 것이고, 하이드로젠과의 본드 또한 이제 sp2 카본과 수소 1s의 인터랙션이 아니라 sp3 하이브리다이즈 오비탈과 1s 오비탈 간의 인터랙션이다, 이렇게 해석을 하셔야겠죠. 어렵지 않죠, 그죠? 그리고 앞에 슬라이드에서 이야기했던 룰은 여전히 적용됩니다. 그래서 제가 아까 유닛을 잘 보라고 했던 말이 론 페어가 되는 순간 이제 암의 개수로 카운트가 되는 거예요, 그죠? 그래서 N아이언 같은 경우에 가바 N아이언 경우에 론 페어도 암의 개수로 취급을 받고, 그러면 싱글 본드 1, 2, 3 3개, 론 페어 1개 이렇게 되니까 토탈 암이 4개가 되죠. sp3 하이브리다이즈 모델을 설명하는 개념과 컨시스턴트하다. Right? That is the reactive carbon species and how these reactive carbon species can be described with the hybridized theories. Then we can maybe extend the principle we just learned to the heteroatoms. Right? So nitrogen or oxygen containing species. Right? And we're getting molecules. You can you will encounter a lot, right? The nitrogen containing molecule, oxygen containing molecules, and how we can describe the bonding between these, right? So we can maybe think about the single one first, maybe nitrogen and ammonia, right? And this is the structure of the ammonia, and you know that ammonia has one lone pair, right? If you apply the same rule, right, you have one lone pair, right, and one sigma bond, sorry, 3 sigma bond, right? In total, you have 4 arms by which you can claim this nitrogen must be sp3 hybridized, right? That's why you need to invoke sp3 hybridization model. Right? The ammonia as a base can be protonated, right? And become, in this particular case, ammonia becomes the ammonium ion, right? And NH4 plus cation, right? It can be also explained, geometry also explained by the sp3 hybridized model, right? In this case, you have 1, 2, 3, 4 arms, right? There's no lone pair, so total, right? 4 arms. So you can still invoke the sp3 hybridized model in this case. Right? So each bond between, right, hydrogen and nitrogen can be described as the sigma bond interaction between one s orbital from hydrogen and sp3 hybridized orbital from nitrogen, right? And there's a lone pair, right, residing in the sp3 hybridized orbitals. Okay. What about oxygen containing species? The typical example is water, right? H2O, and you know that water or central oxygen has, right, 2 lone pairs, right? So you have 1 on, 2nd on, 3rd on, 4th on. Right? So the central oxygen in this case must be sp3 hybridized, right? And there's each lone pair residing on the sp3 orbital. Right? The bond between oxygen and hydrogen can be described as the interaction between, right, sp3 orbital and 1s. You need to invoke, right, sp3 hybridization for the central oxygen. What about halide containing species? Hydrogen fluoride, for example, right? You can invoke, in this case, right, again, the sp3 hybridization. If you focus on this halide fluoride in this particular case, then you can count on, right, count the number of arms here, and you have 3 lone pairs, right? 1, 2, 3, and 1 single bond, right? So 4 arms. So sp3 hybridization for the central fluoride as well. 그래서 뭐 HX 스피시스 할라이드를 컨테이닝하고 있는 애시드 같은 경우도 마찬가지죠. 할라이드 기준으로 보면 론페어가 3개 있고 하이드로젠과 원 싱글 본드를 가지고 있으니까 파이 개수로 보면 4개가 있는 거고, 따라서 센트럴 할라이드는 sp3 hybridization 필요하겠죠. sp3 오비탈에 론페어 하나, 둘, 3개가 들어가 있고, 이 하이드로젠과의 싱글 본드가 sp3 오비탈과 그리고 하이드로젠과의 인터랙션, 1s 오비탈과 인터랙션에 의해서 기술이 될 수 있겠죠. 맞죠? 같은 원리를 계속 적용하시면 됩니다. Okay? So again, for the single bond between this hydrogen and halide, you can use the sp3 hybridization model for this halide. Right? So this single bond can be described as the interaction between 1s and sp3 hybridizer model. Okay? For the fluoride, you need to invoke 2 sp3 hybridizer model. For the chloride, hydrogen chloride, you need to invoke 3 sp3 hybridizer models. And for bromide and iodide, right, you can increase up the number. Right? The size will vary. That's what this slide indicating. Right? This is the orbital interaction. Right? The diagram for the orbital interaction for HF, HCl, HBr, HI molecule. From the left, you will have an s-orbital hydrogen with 2 sp3 orbitals, right, from fluoride. Right, you can see the interaction, the overlap of s-orbital, right, green, of hydrogen with the 5 sp3 orbitals, right. And from left to right, you can rationalize, right, the decreasing electron density in the region of the overlap, right. If you focus on, right, the overlap part, right, as you move on from left to right, that amount of overlap decrease, right? That means bond length is decreasing from left to right. Okay? And what that means further is increasing bond lengths. Okay? These are reciprocal relationship. 그래서 여기 오비탈과 1s 오비탈과의 이제 하이브리다이즈 오비탈과 1s 오비탈과의 인터랙션으로부터 우리의 본드 랭스가 변하고 주기가 변하게 될 때 본드 랭스가 변하고 혹은 다른 말로 본드 랭스가 변하는지 스트렝스와 랭스는 역관계에 있겠죠. 그렇죠? 본드가 가깝다는 얘기는 짧다는 얘기는 인터랙션이 강하다는 이야기고 본드가 강하다는 이야기죠. 반대로 본드의 길이가 길다는 얘기는 그만큼 약하다는 이야기가 되겠습니다. 그래서 이 트렌드를 우리가 하이브리다이즈 오비탈 디오리로 이제 설명을 할 수 있다는 얘기예요. HF와 HCl, HBr, HI 간에 이제 HX 간에 그죠? bond length 혹은 bond strength에 대해서 이제 트렌드를 설명할 수 있게 되는 거겠죠. 그래서 bond length가 HF에서 HI로 갈수록 이제 늘어나는 건 위에 하이브리다이즈 오비탈로 설명이 가능하고 역관계 있다고 했죠. bond strength는 이제 bond length가 줄어들수록 늘어날 테니까 그렇죠? 이것 또한 설명할 수 있다. 오비탈의 크기로부터 이제 1s 오비탈과의 저쪽 면적을 가지고 몰라의 면적을 가지고 우리가 설명을 할 수 있다. Okay, so again, using the hybridization theory, you can guess right, the degree to which each orbital can overlap, and they can translate into the bond strengths and bond lengths. Okay? That's how you can explain right why HF and HI, for instance, have different bond lengths and bond strengths, and there is a trend, right? Right, maybe we can solve the quiz again. So first one, you should notify right the degree of hybridization for the indicated element. So carbon, for instance, what is the degree of hybridization, and nitrogen here. So if you apply the rules that we just learned, you can decide whether this center element is sp3, sp2, or sp hybridized. And the second one, what is the hybridization? The indicator A. Yes, you can identify the number of lone pairs and count the total number of arms, then you can easily answer it. Right? Third one is what orbitals are the lone pairs each of the following molecules. So the question is the character of the hybridization of a given lone pair. Yes. Here and there and here. We can solve together from top left, right? You can count the number of arms. Again, the center carbon has 3 single bond with hydrogen and 1 single bond with nitrogen, right? So 4 arms. So we know that this carbon must be sp3 hybridized. What about this nitrogen? You have 1 single bond, 2 single bond with hydrogen, and 1 lone pair in total. This nitrogen has 4 arms. You can identify, right? So it must be sp3 hybridized. This carbon sp3, this carbon can count the number of arms again, right? You have 1, 2 single bond and 1 double bond. There's no lone pair, so it has 3 total arms, so it must be sp2 hybridized. What about this nitrogen? You have 1 double bond, 1 single bond, 1 lone pair, so it has 3 arms in total. It must be sp2 hybridized. This nitrogen must be sp3. Okay? 1 single bond, 2 single bond with hydrogen, and 1 lone pair. So in total, it has 4 arms. This carbon sp3, this carbon, you have 1 single bond, 1 triple bond. Okay? So in total, you have 2 arms. Okay? So this carbon must be sp hybridized. What about this nitrogen? 1 triple bond, 1 lone pair. Must have 2 total arms, so this nitrogen is also sp hybridized. You can do the same thing for this oxygen. You have 1 single bond with carbon, 1 single bond with hydrogen, and 2 lone pairs. It has 4 arms, right? So this oxygen must be sp3 hybridized. Okay, this gives you an answer for this oxygen, right? But you can double check, right? You have 1 double bond, 2 lone pairs, has 3 arms. That's why oxygen has to be sp3 hybridized. This carbon sp3, this carbon sp2, this carbon sp3. What about this oxygen? This is CO2, right? Carbon dioxide, right? This oxygen has 1, 2 lone pair, 1 double bond with carbon. It has total 3 arms. So this oxygen must be sp2 hybridized. sp2 hybridized for the right hand side oxygen as well. What about this carbon? You have 2 double bond, right? And no lone pair, no bond anymore. So it has 2 arms. So this carbon must be sp hybridized. Okay? 룰 적용하시면 쉽죠? 이게 반복이 되면 이제 첫 보면 아십니다. 그죠? 그래서 연습을 좀 하시면 돼요. What is the hybridization of indicator atom? This carbon. This carbon has a bond with carbon and hydrogen, a single bond, and 1 double bond with the carbon next to it. And there is no lone pair. It has 3 arms. So this carbon must be sp2 hybridized. This oxygen, you already know, right? But you should know this oxygen has 2 lone pairs. Right? If you think about the octet, right? And you have 1, 2 lone pairs and 1 double bond, right? Has 3 total arms, so this is sp2 hybridized. This oxygen sp3, we already know. You have 2 lone pair and 2 single bond, 4 arms. This nitrogen, right? You already know. There's 1 lone pair to satisfy for the tap. So you have 1 triple bond, 1 lone pair, 2 total arms. So this must be sp hybridized, right? These are the same molecule, by the way. Okay? So you already know this lone pair then sp hybridized. What about this nitrogen? You know that there is 1 lone pair, so you can count total number of arms and for this oxygen, you can also count the number of lone pair and answer the question. And you can do the same thing for the bottom one. 그래서 뭐 크게 어려우실 거 없어요. 룰을 적용하시고, 그리고 룰을 적용하기 전에 먼저 하이브리다이제이션 원리를 이해하시면 되겠죠. 뭐 이해하시는 게 그렇게 어렵진 않을 거예요. 그랬을 때 이제 론 페어 혹은 엘리먼트가 취해야 될 하이브리다이제이션 정도를 이제 그 모델에 적용하셔서 아이덴티파이 하시면 되겠죠. 연습 문제를 좀 많이 풀어보시고 익숙해지시면 이제 첫 보면 아시게 될 겁니다. Right, this is a summary how the hybridization model can explain the geometry of the molecule and what the bond lengths and strength of bond means. The shorter the bond, you know that the bond is stronger. Right? So you know the triple bond is the shortest bond, right? And why triple bond has the shortest bond in the first place? Right? You have one single bond and two pi bonds, right? And for the double bond, you have one single bond, one pi bond. There's one single bond, right? So that's why the single bond is the weakest bond, or the longest bond. The more bonds holding two atoms together, the stronger and shorter it is. Those are general features that we already know. The greater electron density, stronger the bond. So if you compare carbon bond and carbon hydrogen bond, right? The carbon hydrogen bond has a greater electron density in the region of the orbital flap. That's why the CH bond in general is a shorter and stronger bond. Okay? And this can be rationalized by the degree of S character as we mentioned in the above slide. Right? So this carbon is sp3 hybridized, this hydrogen is s orbital, right? The pure s orbitals. So in total, we can think about the net s character describing the bond between these two elements, right? And this has to have higher s character. That means the lapping area is more electron density, right? And which make the bond, the corresponding bond, more stronger. Same thing, more S character, shorter and stronger the bond, right? That's how you can characterize the bond between carbon and hydrogen, and each carbon has different degree of hybridization. If you can think about this molecule, and we are comparing the CH bond, right? And as the S character is rising, increasing, the corresponding bond becomes shorter and stronger. 반대로 그렸네. 그죠? It must be the opposite. This must be the part of acetylene, for example. This must be the part of So if this carbon is sp hybridized, then the S character must be 50%, right? Then we describe the bond between this carbon and hydrogen as sp and s interaction, and this one is sp3 and s interaction. So in net, right, this must have higher S character, thus shorter and stronger the bond. Okay? And there's a trend: the more the S character, larger the bond angle. This can be explained by the hybridization theory, right? With the sp3 hybridization, you know that each central element has tetrahedral structure. And the bond angle thus become 109-ish, right? Degree. And as the degree of hybridization increase from sp3 to sp2 and sp to sp, right? The bond angle change, right? From 109-ish to 120-ish. And 180, right? It's bond angle increase. And applying the principle we just learned, we can rationalize and answer this question as well, right? And maybe you can solve the bottom one as well. And if you can identify the missing lone pair, then you can decide the degree of hybridization for each element as well. So this is the practice questions you can solve by yourself. And about this, what is the hybridization of each of the carbon atoms in the following compound, right? And I'm sure you can answer the questions. sp3, 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 sp2, sp2, right? sp3, sp, sp, sp3. Right? So you can double check for yourself. What is the hybridization of each atoms in their role in project? Right? This is the structure, right, of the molecule. And I'm sure you can solve this. sp2, 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 sp2 rows. This is sp2, right? sp2, sp3, right? sp3, 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 sp3. 그래서 뭐 익숙해지시면 그냥 이제 바로바로 하실 수가 있어요. 프로젝트도 마찬가지로 한번 해보시고 연습을 해보시기 바랍니다. Right, that was about the chapter 1 stuff, right? So to summarize, we learned about today the hybridization theories, hybridization models, and on how these models, right, can be used to explain and rationalize the structure of organic molecules, okay? Which are going to be very, very rudimentary to predict and explain the reactivities of a given molecule as well, which we'll learn in the subsequent chapters. Okay. And we still have 5 more minutes, so maybe I can into the acid-base chemistry, which is again quite Gen Chem stuff, and pretty much sure you guys all heard about, right, these topics. So what is acid and base? And you know that there are multiple definitions, and one of the most famous definition is the Bronsted-Lowry definition. Okay? What is acid in this framework, in this definition? Acid is the proton donor, base is the proton acceptor. So for this reaction, right, the reaction between HCl, hydrogen chloride, and water, and designate which one should be acid and base, right? So HCl is acid, as you know, right? This acid loses a proton, or in other words, donate a proton, right, to the water, right? So water accepts the proton. Right? As a result, you are generating the chloride anion, right, and hydrogen cation. So water accepts proton to become hydrogen, right? And if this acid-base reaction is reversible, then you can also think about, right, the backward reaction. And in this case, the hydrogen cation serving as an acid by donating proton to the chloride anion, right? So in this case, right, acid loses proton, base gains proton. So you will encounter on the next slide the pairing concept. But in the Bronsted-Lowry definition, any species that has hydrogen can potentially serve as an acid, but any species that has a lone pair, right, can potentially act as a base because the lone pair can accommodate the proton. Right? But there are empathetic species, which is water, right, can become, right, base or sometimes acid. Right? So water, for instance, from left to right, serving as a base, right? But in its conjugated form, hydrogen is serving as an acid. So we will learn about, right, the conjugate acid and base concept in this definition as well, right? And then acid-base reactions at the front of the label as a reversible, right? So proton donation and back donation can be reachable, right? From A react with B to become C to D, and if the reaction in general is reversible, that means C react with D can go back to A and B, right? So this is general definition for the reversible chemistry, reversible reaction, and that applies to the acid-base reaction, right? Acid-base reaction is the first reaction you learn, right, for the organic chemistry, right, in this chapter. Okay, proton donation to water, right, and proton donation from hydrogen ion to chloride. That's irreversible, meaning that forward and backward reaction can both be feasible, right? And there is a pairing, right, or conjugation, right? HCl and NCl minus can be a pair, water and hydrogen ion can be a pair, right? So conjugate acid and base concept arises within this definition, right? The Bronsted acid and base definition as well, right? And this is also the ZenChem stuff, right? For quantifying, right, or evaluating the acidity of a given species, we define the following constant, the acid dissociation constant Ka, right? And its constant can be also evaluated in a log scale, minus log scale, which is a pKa, right? And you know that larger the Ka, right, meaning smaller the pKa, the corresponding species has a stronger acidity, right? The stronger the acid. Right? And this is a scale of the given solution and its pH range, right? You know, the HCl, its pH is around 1 molar pH will give you around 0 value for pH, right? 0.1 molar will give you around 1 as a pH, right? The smaller the number, stronger the acid, larger the acidity, right? And this is the general formula for the acid, right, protonation reaction. A species give proton to water, right, to generate hydrogen cation and conjugate base, right, A minus, and the K equilibrium, right, the equilibrium constant can be written, right, as the following, right, 0 all down, which we learned in the ZenChem stuff. But the Ka, for the Ka, you only need water, right? This is the definition for Ka, right? K equilibrium times water, right, will give you Ka, but water term is here basically constant. And if you take right the minus log for the Ka, and that will give you pKa, right? That's the general relationship between Ka and pKa, right? And you can apply this to right the tone concentration and pH as well. So minus log, right, H plus concentration will give you pH, right? That's why this trend, even stronger the acid, larger Ka, smaller the pKa. It's all what you know, really. But what you need to know, right, for the organic chemistry is the general, right, trends and maybe the ballpark number, right, of the pKa for a representative molecule or the functionalities, right, within the molecule, right? And this is a typical pK values of the functionalities appear in organic molecules, right? So you have protonated alcohol, right? OH2 plus ladies, as you can guess, right? It's pretty acidic. The pK value is minus 2.5, meaning the species can give proton to other species very well, right? It's very acidic. Protonated alcohol is very acidic, right? And protonated right, carboxylic acid is also very, very acidic. Right? The neutral form of the carboxylic acid, right, its pKa is around 4. You better know this number. Right? What about amine and protonated amine in particular? Its pKa is around 10 or 11. The neutral form of alcohol, as you probably know, its pKa is around 15 or 16, and you know the value for water, right? And methylamine, pKa is 40, ammonia 36. Right? This is the approximate pK value table. Okay, the protonated alcohol, water, or carboxylic acid, very, very acidic. Its pKa is below 0. Whereas the carboxylic acid, the neutral form, its pK value is around 4 to 5, and protein amine around 10, and neutral form of alcohol and water is 15 or 16. So you'd better know this number, right? And then you can guess, right? These species must be acidic or basic. Right? 그래서 뭐 디테일하게 넘버를 다 외우실 필요는 없지만 볼파크 트렌드 정도는 아시면 좋죠. 그죠? 알코올이나 카복실릭 애시드가 프로토네이션 돼 있다. OH2 플러스 혹은 OH 플러스 모이어티가 있는 경우에 그 경우에는 아주 애시딕한 사이트로 작용하게 되겠죠. 프로톤을 잃고 난 이후에 중성 봄이 안정하니까 그렇죠? 프로토네이션 돼 있는 그 주체 애시디티가 아주 높겠죠. 그게 브론스테폴리 S 베이스, 컨주기 S 베이스 우리가 아마 다음 시간에 조금 더 이야기하겠지만 페어리 컨셉과 이어지는 부분이고 뉴트럴 폼은 이제 알코올인 경우에 워터인 경우에 pK는 15점. 그러니까 프로토네이션이 한 번만 되더라도 그 사이트의 애시디티가 엄청나게 증가하는 거죠. pK가 유닛 하나 증가한다는 얘기는 로그 스케일로 하나 증가하는 거니까 10배 좋아지는 거예요. 15가 바뀐다는 얘기는 오더가 15가 바뀐다는 얘기예요. 그러니까 애시디티가 상상할 수 없을 만큼의 숫자로 증가한다라고 생각을 하시면 되겠죠. 그렇죠? 카복실릭 애시드는 4에서 5 정도. 그렇죠? 그러니까 pretty acidic하죠. quite acidic하다고 얘기할 수 있을 것이고 아민이 아니라 프로토네이트 아민입니다. 그래서 나이트로젠 사이트에 하이드로젠이 이제 하나가 더 붙어서 아민이 프로토네이션 됐을 때 이때 pK는 한 10 정도가 됩니다. 그래서 이 정도 밸류는 기억을 하고 계시면 좋겠습니다. 그러면 여기까지 하고 다음 시간에 이어서 3년기 마무리하고 챕터 3로 들어갈 수 있도록 하겠습니다.